Today, we're going to start our session off with two gentlemen. First one is Jesse D'Aguanno, and the second one is Timo Teräs. Did I say that right? Perfect, perfect. So their talk today is going to be a touch of pawn, it's going to be incredibly enjoyable. I hope you guys enjoy yourselves. If you have questions, I'm going to ask that you save them till the end. And when I say the end, I mean 3:15 in the villages. So we're going to have the villages kick off about 3:15. There's going to be a little bit small session around lunchtime, but we're really going to ask you guys to join the lightning talks instead. But 3:15, that's going to be a perfect time, MSRC Village, where you can ask your questions and steal their time away from them. All right. So without further ado, let's get started.
All right. Thank you, Bruce.
My pleasure.
Morning, everyone. Like Bruce said, I'm Jesse. This is Timo.
Hello.
And today we're going to tell a story about attacking Windows Hello fingerprint authentication. So a little background about who we are. Timo, who are you?
Just a random guy from Finland, doing security research with Jesse, working also on Alpine Linux stuff. For fun, reverse engineering, catch the flags, and of course sauna.
Yep, lots of sauna.
But Jesse, who are you?
My name is Jesse D'Aguanno. I've been doing security research for a little over 20 years. Again, similar interests, I think, reverse engineering, vulnerability research, things like that. So what we're going to talk about today was actually some research that we were handed by Microsoft's offensive research and security engineering team, the MORSE team. And the mission was to do vulnerability research on the Windows Hello fingerprint authentication. So the top 3 fingerprint sensors or embedded devices with fingerprint sensors for Windows Hello were chosen, selected originally by the Windows Hello team. And the goal was to see how easy it would be, or if it would be possible, to bypass Windows Hello authentication. There was another little element to this, and a lot of the background research that there's been published about biometric authentication and biometric hacking, fingerprint hacking, is really around creating fake fingerprints, cloning fingerprints, things like that. We actually did have a little bit of an element to that and had some interesting results, kind of less in our direct wheelhouse as far as vuln research, but pretty fun. That's not what we're going to be talking about today. Today we're talking specifically about software and hardware attacks against the embedded sensors and the host. So this was black box, so no source code available. All of these sensors are third party. Just had 3 brand new laptops. So our process involved a lot of reverse engineering, vulnerability research, hopefully exploit dev if we could find some. And that's what we're going to talk about.
I remember initially when you explained that we have potential here, I was like, hey, that's easy. 10 years ago, I did reverse one fingerprint reader. It's fake crypto, and it's just like scanning your fingerprint, and that's it. We just replay that, and we are
good. Just replay an image, go on with our day. That was kind of the initial thought, because a lot of the state at some point was pretty bad, right? So we'll see if that assumption played out. The threat model that we're operating under, we are assuming physical access to a target. So something like a stolen or confiscated device, an evil maid attack, that kind of an attack vector. And the goal, again, was to bypass Windows Hello authentication. One part of the model that was explicitly out of this threat model was like local privilege escalation, using the Windows Hello fingerprint subsystems to elevate as an authenticated user to system or something like that. That was not part of this research. So targets. These were, again, the top 3 Windows Hello devices that support fingerprint authentication that were chosen for us. So The first one was a Dell Inspiron 15, which after digging into it, we found had a Goodix sensor. What was the next one, Timo?
Lenovo ThinkPad T14S with the Synaptics sensor.
Yeah. And then finally, the flagship Microsoft Surface Pro. In this case, the Surface Pro X with the type cover, the fingerprint type cover.
Version 2.
Yeah, so version 2, yeah. So those were our primary targets there. One common denominator among all of these targets is that they're all match on chip. What does that mean?
So basically, the assumption we had that it would scan your fingerprint and send it for the host to be analyzed, that's actually happening on the sensor itself. Your fingerprint never leaves the sensor to the host computer. Instead, there's some magic on how it does the matching. If it matches something already in the sensor, then it just sends to the host that, okay, this one I know, and then the Windows host can attach also some data on the fingerprint to identify who that person is.
Right. So right out of the gate, our assumption of the sensor actually just being a capture device that sends to the host for matching is kind of blown out of the water, right? So all of the matching is done on the chip. So if we're going to attack it, we need to attack the chip itself.
Yeah. Things do happen in 10 years.
Yeah, thankfully. Yeah. And one little side, the Windows Hello Enhanced Sign-In Security only supports this type of chip, as opposed to match on host, which is kind of the other type of sensor.
Yeah.
So what is Windows Hello Enhanced Sign-In Security? There's a number of goals that are stated by Microsoft. First of all, protecting biometric data at storage or at rest. So like Timo said, biometric data, fingerprints never leave the chips themselves. So they're not sent to the host. So from a privacy perspective, that has some protection. And there's also the intention of a secure communication channel, making sure that the sensor is actually, and the communication between the sensor and the host is secured in some ways. This is made up by a number of different components, one of which is the Secure Device Connection Protocol. And that's a protocol that was designed by Microsoft for this specific use in order to prove the integrity of the sensor and things like that. So we're going to go into a little bit more detail of what SDCP is. Timo, you want to kind of walk us through that one?
So SDCP is a specification, not a full USB protocol specification. It's just like having pieces that the device needs to do, pieces of data that needs to go back and forth between the host and the sensor. The goal is to have end-to-end secured channel. So when the sensor boots up, it's actually validating the firmware version, calculating things, generating a session key for the runtime. And then SDCP will define on how to do the crypto that Windows can authenticate the sensor as running a valid firmware. And it also has a specification on what needs to go together with the enroll and identify actions so that it cannot be replayed at all. And it can be guaranteed that it's a genuine connection and from valid, trusted sensor.
Right, good. So yeah, it goes back to a root of trust certificate that's issued by Microsoft. And so the firmware needs to be is validated for the integrity. So to make sure that the sensor is not just a spoof sensor, things like that. And then also the communication between the enroll process, enrolling a new fingerprint, and identifying whether the fingerprint that's being presented is actually an authenticated user, is all signed, and there's some crypto, right? Mm-hmm. Okay, so we'll walk through quickly kind of the process that SDCP. First, there's a bootstrap process when the device is first plugged in, or if in these cases they were all embedded devices. So when on boot up, SDCP creates a session with the target device, this target sensor. So the Windows host does some initialization, makes a connection. The sensor hashes the current version of the firmware and makes sure that it's not been tampered with. essentially there's a key agreement.
Yeah. And then the sensor also signs with the Microsoft approved or signed certificate.
Yeah.
Everything that it's trusted.
So once this process, we're hand waving a lot around this process right now. I mean, to boil it down into a single slide with that you can read. but yeah, this is essentially the process in order to build up a secure connection.
Think of it as TLS handshake.
Yeah. Without the encryption.
Yeah.
Okay, so here's the enrollment process. Essentially, the Windows host begins an enrollment, and again, there's kind of a dance between the Windows, the host, and the sensor, and the user ends up enrolled with fingerprints in the database of the sensor that's tied to an ID. That the sensor knows about and that the Windows host knows about. There's a message. There's a MAC that's involved there, that's tied to the session between the host and the sensor, and so that there's integrity checking at that point. But then later, that MAC is used just as a static ID for that template in the database. Yeah.
And one of the big assumptions here is that this is the only way to generate IDs. So basically, neither one of these has direct control what the ID will become, because it's basically a MAC of the nonce.
Right. So Timo's foreshadowing some of the things that are to come. But yes, there's an assumption here that the only way of getting a fingerprint into the database and generating those IDs is through this authenticated process, right? And how about identification? How does that work?
So then the Windows host will generate the nonce. The idea is that no one can replay anything because the nonce is generated by the host. It's sent to the sensor. When it has actually captured the sample, done the database lookup, it will take the ID, which used to be the MAC, now it's just the ID of the finger, calculates a new MAC based from that ID and the nonce, and sends those back. So basically there's the finger ID and MAC ensuring that it's not replayed.
Yeah, so just to kind of underscore that point, what is the purpose of that? Why is that MAC happen?
Two reasons. We cannot just record something and replay, and also that we cannot just swap the sensor in between the communication. It also guarantees that the sensor is still the sensor we originally connected to.
Right, exactly. So replay of like observing the bus and replaying it to the host is not able to be done, and same with kind of once that session's built up, it's tied to that initial session, right? This is all part of the Windows biometric framework, and we're not going to go into a lot of depth. But Timo, what do we want to highlight about where SDCP really is focusing?
Yeah, I wanted us to have this slide here because in the biometric unit, that's the different APIs the biometric driver needs to implement. It has sensor, engine, and storage adapter. SDCP basically covers the sensor and engine adapter in like pieces of those, but not fully. And the storage adapter side is basically not covered by SDCP at all, because this model is based on the match on host thing. You see the template database is in this diagram actually an outside entity, whereas in match on chip implementations, the template database is inside the sensor.
Yeah. So we're starting to see a picture of SDCP is actually overall pretty well designed, but it's pretty limited in scope as far as the overall interaction between the host and the sensor. So as vulnerability researchers, that's usually where we start focusing, is where are those limitations, where's the bounds of those limitations and the edges, right? So just as a kind of an explanation here, if you've logged into to Windows before and Windows Hello with biometric auth, like a fingerprint auth, you see this icon giving you the option to log in with Windows. And this is actually, why does this do this? What enables this, and why is it useful for us?
You actually see that icon only and only if the sensor is connected. So for example, on the Surface, which has detachable type cover, if it's removed, the fingerprint disappears because the sensor is not connected, so it's not available. And to make that happen, that's why the storage API needs to know which fingerprint IDs are available at the moment.
Right. Yeah, so this is actually, it's built in by design. The architecture actually requires the ability to query a sensor and list out, essentially leaking out what IDs the fingerprint sensor knows about. And that will become useful too later. So again, that was kind of our initial analysis. A lot of initial reverse engineering to figure out what do we go after first. Identification of what bus, because we didn't know they're embedded sensors. Are they USB? Are they some other unknown proprietary bus? Reviewing the system configurations, things like that. Also, a quick assessment of the code quality of the different drivers to figure out what should be our priority as far as from a vuln research perspective, right? And then going on and actually doing the research on the different targets. So this is what we came up with as far as a priority list. Number one was the Dell, the Goodix sensor. First of all, it supports SDCP. There's good support for Linux, right?
We found out the Goodix people were nice enough. They implemented the whole thing in the Linux libfprint. So we actually had a documentation of what the protocol is doing. It's clear text USB communication. And that really helped us on the initial analysis to see also what the Windows side is doing.
Yes, and as good code sommeliers, we gave it the sniff test, and it definitely had some smell as far as code quality. So that was that kind of pushed it up as far as priority. We thought this might be a quick, easy win, and then we moved on to the more difficult targets, right? The other targets, like the ThinkPad, had limited Linux support. It also was supported by libfprint, but in a limited way. We also noticed that the USB traffic was encrypted. So again, in order to inspect that, we'd have to actually break the crypto or something like that.
Basically, on Linux side, they used something completely different. If you put up Windows sniff, it's like everything's encrypted. It's completely different implementation.
Yeah. And then finally, the last one, which was the Surface Pro, we were a little bit scared about that one because, first of all, what we were given, or what our initial target was, a Surface Pro X. So as an ARM, Windows on ARM, the tooling is a little bit funky. So trying to get some of our tooling even to just like USB mon and things like that in order to watch USB traffic, a little bit more difficult. And then also it's a Microsoft flagship product.
And then the hardware connector, completely proprietary. We cannot really also sniff the hardware side of things either.
Right. So we'll come back to this, but here's a Surface Pro, and it has it's detachable. And you've got this little connector. We don't know what that is, those kind of things. All right. So the first target, the Dell, internal USB, match on chip, supports Windows Hello and Linux. Our goals are essentially first looking at the configuration. What do the drivers look like? What is the config on on the Windows side? Examine what was available of the Linux drivers. Try to observe the host to sensor communications and try to make sense of that. Reverse engineering a proprietary protocol, and then focusing on reverse engineering the drivers to build a bigger picture. Potentially the firmware as well. We'll get into that a little bit more. The firmware we didn't focus on as much with this particular research reversing because all of the firmware blobs were encrypted. There are ways that we could potentially get the keys out of the sensor, but we focused instead on the host side and the protocol.
Yeah. So as mentioned, the Linux driver, the Windows driver, were doing pretty much the same thing, and we wanted to analyze if there are any differences because we know for sure Windows side did SDCP, the secure thing. On the Linux side, it really didn't. So let's see, to recap, what did the Windows side do?
Go ahead.
It follows the SDCP. This is the same image we showed earlier. It follows exactly this, what the SDCP documentation says it should do.
Unfortunately, the Linux side doesn't support SDCP, right?
Yeah.
So
that was the implementation. They basically deleted everything that's related to the security.
So this is where we have the "this is fine" meme, but we had to have legal, I think, pulled all those things out. So yeah, all the security, they implemented the rest of the protocol except for the security.
Yeah,
right?
and one thing to note here is that on the sensor side, they also changed things. It no longer validates the ID, which was mentioned that is actually enforced by SDCP, that it needs to be validated to get something rolled in. And basically, this means that on Linux side, we can enroll anything with any ID we want.
Yeah. So basically, looking at this, we have an idea. We think, okay, so the sensor is holding the templates. On the Windows side, the IDs are generated cryptographically and then stored into the template database. But with Linux, we can give it whatever we want. And so we can potentially list the IDs that are in the database, enroll an attacker's fingerprint as spoofing that ID, give it through the Linux driver, store it into the database, and we're golden. Then we can authenticate as the the target user with an attacker's fingerprint, right?
So we thought this is like how the implementation looks like.
Yeah. Unfortunately,
it wasn't
work.
like that.
Yeah.
No.
So the chip actually has two separate databases. There's a Windows side to support SDCP, and the ID generation is actually, the cryptographic ID generation is enforced. So if it's going through the Windows SDCP, it stores it in a separate database. There is a little bit of weird data leak, but we won't go into that. And then there's a separate non-Windows or Linux template database where if you're authenticating on the Linux side. So we couldn't just enroll on the Linux side and auth on the Windows side. But then we started thinking, okay, how does the sensor know which database to use, Linux or Windows, right?
Yeah.
So
turns out in the very beginning of the handshake, there's one config packet it sends. There's 1 byte that tells which database to use.
Yeah. So when the sensor is plugged in or the host comes up, a configuration packet goes across with a number of different config details, including how sensitive should we be as far as the fingerprint, things like that. Yeah. But what database to use. And so there's a flag for Windows or a flag for the non-Windows database. And this packet is not authenticated, right?
Yeah.
Yeah.
Of course not.
So anybody
have any ideas?
So basically, here's this packet. Basically, when Windows comes up, a config packet says use the Windows database, and so the sensor is using the Windows database. And that's not per other operation. That's one time per boot, basically.
Yeah.
So then it's persistent. So it's authenticated. The enroll and the identifier are authenticated then against the Windows template database. Again, the identification, this is just a refresher from what we talked about before.
So the question then became on the Linux side, what would happen if we have SDCP connection established and we would do identify? Would the sensor calculate the actual MAC regardless of which database was used to authenticate against?
Yeah, so that's right. So basically, if we can rewrite the config packet and enroll our fingerprint with the right ID into the Linux side, and then rewrite that config packet so that the Windows side is actually pointing at the Linux database, would this still happen? Would the MAC actually still happen so that Windows would appropriately authenticate? And the answer is yes, it does. So we were able to prove that out. How did we prove that out?
So you actually did some deep WinPack magic. We reversed the location where the config packet is constructed. We hooked it up and modified that 1 bit, and then let things go. And we had basically Windows identify against the Linux database.
Right, and a Scotch at that time.
Yeah.
So we have an end-to-end. We've proved out that you can enroll an attacker's fingerprint as a target user in the Linux database. We can rewrite the config packet to point Windows to the Linux database, and then you can authenticate. Unfortunately, I mean, it's all proven out, but like Timo said, we're doing this in a debugger at this point in order to hook that packet and rewrite it. So all we have left is really just to weaponize this, right?
Yep.
All we need is a USB man in the middle, so that we can, between the sensor and the target host, rewrite that packet, and then we're done.
Yeah.
So just to recap, the vuln chain here is there's an info leak. We enumerate what templates are in the database, the fingerprint database, and then we can arbitrarily write to the Linux side, and then we can point Windows to the Linux side and authenticate as that user, right?
Yep.
Okay,
next
so we
slide.
already talked about
Yeah.
that. So USB research.
We basically looked into what's the big thing, how to do USB man in the middle. You found USB proxy, but it was kind of dead. So the thing at the time was GreatFET1 and Phase Tensor as software stack.
Yeah, that's basically kind of like, USB research, like tooling and things like that. This is where everybody kind of, it seems like the hotness right now, right?
Yep.
There's a cool demo video. It makes it really easy with Phase Tensor to MitM something. You use the GreatFET, and with Phase Tensor with Python, you can basically just observe packets and then rewrite them. There's a demo where I think they are inverting the controls on a Nintendo Switch inline, and so they MitM the protocol between the controller and the Switch.
So, sold, we bought one.
Yeah, so we did it, hooked it up, wrote the exploit real quick.
Did the hardware development to actually adjust the voltage?
Yeah, this is embedded USB, so we did have to do a bit of Frankensteining and a bit of hardware reverse engineering to figure out, okay, how can we rehost it to be able to be pluggable, so we can.
We did that. We connected. It should work. It did not even connect, and we're like, it's supposed to work. It's not working. What's the problem?
Yeah.
And we dig deep down into the USB, and turns out in USB bulk transfers, there's a thing called zero-length packet, and apparently none of the developers get that right. What it means? It's when when the host is reading data from USB device, it will tell what is the maximum length of that transfer it can accept. If it's something small, say 64 bytes, then you just get one USB packet back, and that's it. If it's going to be long, like 16 or 30 kilobytes or something, the maximum length, then the device can keep sending packets of maximum length. It's always maximum length until the final packet. If it's less than maximum length, then it's like indication that this is end of the transfer. And if it happens that what's being received actually aligns up with the maximum length, in that case, a zero-length packet is sent to indicate that, okay, this is the end of the transfer. If you would not send that zero-length packet, the USB transfer would time out, and it would return error condition all the way back to the drivers, and nothing works. That's what was happening. The Phase Tensor software was not passing through the zero-length packets, and it was also not really handling the whole transfer thing at all. It was handling packets only, and if we had like really long transfers, and we really wanted to go and do the MitM stuff on a transfer layer, not on the packet layer.
Yeah, so the state of USB research tools right now is pretty poor, and we found out against like real targets, it just doesn't work very well. Like, at least what we were trying to do. So we had to kind of invent our own.
Yeah.
So instead, we actually did it ourselves using a Raspberry Pi, and we'll get into that. Yeah.
Yeah.
So again, this is just the overview of our attack. We rewrite the config. And then the identify goes against the Linux template database instead of the Windows template database.
Okay.
So we're going to demo that. So we've got a bit of a Frankenstein. We'll try to see if everybody can see here. But
do we take the whole thing?
Sure. Yeah.
Disconnect this one.
Yeah.
Okay.
So.
Oops.
Got caught. Okay. So like we said, we had to rehost the internal USB to be able to plug it into the external so that we can use our MitM. Right now we just have this so that we can start the attack, but really this is none of this kind of open Frankenstein-y stuff is really necessary. You could just take a machine and pop open the bottom, extract the actual sensor itself, and plug it into this rig. So what we're going to do here first is we're going to log in, and we're going to set up our fingerprint.
I'll be the victim.
Oh, we've got to probably show people.
Yeah, type in. So it's empty, and now we just add my victim finger. All set.
Okay. So now we can lock. Where is it? And just let's see. I'll log in as the attacker.
Nope.
I'm not legit.
I'm still
Timo
good.
is. So what we're going to do is we're going to unplug our fingerprint sensor and plug it into.
Man in the middle.
We're going to have to switch this around, but our little man in the middle device here. And I'm going to enroll my fingerprint. Now we wait a second. So now my fingerprint has been enrolled. Our MitM is now plugging it back into the Windows host, so completing the connection here, and then so authentication bypass. All right, sweet. One demo worked.
Yeah, that's cool.
Guess we can go
1
home.
out of 3. That's
All
not
right.
bad.
Yeah. Cool. So we had one target done. So on to the next target, right?
Yep. That was the Synaptics one.
Yeah. So this is the ThinkPad. This one again, match on chip, limited Linux support, encrypted communication between the host and the sensor, and also encrypted firmware. So made like firmware reverse engineering a little bit more difficult. We had to focus on reversing the Windows drivers and try to see what we could understand about the on-the-wire USB traffic, right?
Yeah. So basically, we had the same idea, same approach as with the Goodix one. We just reversed the protocol. Turns out it's encrypted by TLS, the actual protocol between the Windows driver and the sensor itself. In the beginning, there's something unencrypted, but after that, it's like TLS. And basically, that means we need to somehow break TLS to be able to look into the data what we have. We are not going to go too much in detail here.
There's a lot of work here. So this was the bulk, actually, of our research.
We spent most of our time.
Very in-depth reverse engineering the protocol and the driver. There was a lot of, with each of these, we also, in order to understand the USB protocol, had to develop custom Wireshark dissectors in order to be able to visualize. We'll show some of that in a second. With this one, because it's TLS, a custom TLS, we also had to develop, basically the ability in Wireshark, the dissector.
So the first thing was we needed to extract the TLS case. How did we do that?
So basically, that was dynamic instrumentation using like Frida in order to extract the master keys in order to
So
be able to,
we took USB captures, and then we had tooling to extract the TLS keys, so we could like decrypt on the Wireshark to see what's going on inside. This is like a couple of screenshots what happens, or like how the protocol looks like. This is the response to the initial reading. Actually, it was pretty clever how the Synaptics does the connection between the driver and host. On the very initial time it's connected, they do pairing. And the host will have the sensor write a certificate back to the host. But because both the Windows driver and then the BIOS implementation of the same thing, they needed to talk to the sensor in a trusted way, they actually ended up putting the private key and the certificate signed by the sensor to a flash block inside the sensor in an encrypted way. And that's a dump of the reading of the flash data. It's being decrypted here as well to show that there's the private key certificate and things like that.
So just to reiterate, there's this custom TLS stack, but it's also not, it's broken.
Yeah, so that's shown here.
Yeah.
When the TLS is started, there are certain elements in the tags that are broken. And it turns out that in the key derivation as well, they mixed up some things. That's, if you do crypto yourself, always verify against third party. They didn't do it, obviously. So, they just implemented the broken thing on both sides. And then we just needed to re-implement the whole TLS in Wireshark to be able to see what's going on.
Yeah, so unfortunately, the crypto breaking there, the implementation problems, didn't lead to a break in the crypto.
Yeah.
But what it did prevent us from was using things like OpenSSL or just standard TLS libraries in order to perform our attack or to dissect, to hook through, with like Wireshark dissector. So had to re-implement their broken stack in both our exploit and the Wireshark dissector.
Yeah. Well, finally, the identify response is here. That's from the default install of the device. And you can see there's SDCP length 0. SDCP was not turned on. And it just knowing the SID was enough to be identified.
Yeah, so
That was kind of,
So going through this whole time, we were under the impression that this target had to be SDCP. That's what we understood. That's also what the Windows Hello team understood. We were on the phone with them and things, and the reversing. The SDCP stack is all there. But we just were not seeing the communication of SDCP, and so we kept digging, going back to the Windows Hello team, things like that. Turns out that the stack is there. It has the ability. It's just not turned on by default, right?
Yep.
So we had to do a bunch of code coverage in order to figure out finally, this isn't getting hit.
We know how to turn it on now, but for the purpose of the engagement, it was off.
Yeah.
So we basically then had same idea as before.
Yeah, so essentially the same kind of attack where SDCP is not actually in the mix here. So as long as we can talk to the chip and establish a TLS session, then everything beyond that is the authentication between the host and the chip. So the driver and the chip assumes that the only thing that can talk to the chip is the established driver.
If you know the private paired key, then you're good to go.
Right. So how did we get the key?
Well, it's encrypted. And if you know the symmetric encryption key, you can get the key.
Yeah. So what is that symmetric key derived from?
It's taken from BIOS because both the Windows and BIOS needs it. So they just took the BIOS product name and product serial number.
Right. So how could we find the serial number?
It's easy. We can read them using code. But what if I don't have physical access to boot?
Oh yeah, it's right here, right?
Oh yeah, it's there printed on the laptop. Yeah, we are good to go even on external device.
Yeah. So we had another attack. As long as we could talk to the chip, build up a valid TLS session, then we should be good as far as enrolling our own fingerprint as the victim and then authenticating as the victim, right? So let's demo that.
There was one slide, but we explained it. So we are running out of time, so let's demo.
We had about 5 hours of content here, so we had to slash quite a bit. But, okay, so I actually just enrolled my own finger here as the victim user, and I'll show that in this case, Timo cannot authenticate his finger.
No.
But I can. Right? Okay, so now I'm off. So, as an attacker, what we're going to do is we're going to...
So for this demo, we could just take the thing out and rehost it on another computer. We did not have two computers here with us, so we are booting the Linux here. That's where our custom code to talk to the chip is.
So we're rebooting, and we just have a Linux partition. Again, like Timo said, this could be a USB stick to boot over to Linux, or just take the chip out and plug it into another machine. But we're going to boot into Linux.
That's going to take a while. Then.
So
how about we show the other demo while the thing is booting?
Yeah, sure. This one was the, again, we were kind of afraid because it's the Windows Surface. It had this proprietary, bus and things like that. So we kind of pushed this off to the side. We really didn't have much time.
We had like just a few days left on the final target.
Yeah.
Well, basically the Elan chip, if I explain that briefly.
There you go, why don't you enroll yours?
Okay.
All right.
A little bit slow today to wake up. Not enough coffee on the computer.
Did you pass that yesterday?
Huh?
Did you pass that yesterday?
No, we have not passed this. You want to talk about the last one?
So it's also
While
a
it's coming
chip, like we showed, custom bus, custom hardware connector, Microsoft branded. Looked like we cannot have the tooling and get it on. Turns out the protocol between these guys is fairly simple. It did not have SDCP on, and it's basically the discussion is like, do you know this SID? It's basically to make sure that it's talking to the right type cover. If the sensor says yes, the driver will ask how many fingerprints you have. I guess that's kind of like anti-tamper detection thingy. So
Make sure that you can't you plug it into another.
Covers, both of these are related to that. And then finally, the identify is just sending back the SID it matched, which we know from the beginning. So could possibly anything go wrong? Yeah, we basically can just record the SID. Then we can query the fingerprints if we want, and in the final identify, we know what to send back if we want to spoof that. But
another off bypass.
yep. Now, for the final target, it turns out, software-wise, it's the simplest thing to do, and we already built all the USB gadget stuff to do man in the middle and other things. So we were like, okay, we just take that and make it talk this other protocol. It didn't work. Turns out that on the USB device descriptor level, there's a bit that says it can do wake up of the device, and the Linux kernel does not support that for the gadget mode. So it did not accept that, and we had to actually go and figure out other APIs like the raw gadget driver to implement the same thing on Raspberry Pi. Unfortunately, the Raspberry Pi boots like a minute or two, and we knew we are going to run out of time. So we implemented the thing on a USB Armory in Tamago, so we can make it run fast enough here. So we have a surface. There's one finger enrolled, you can see. And
It's a complicated exploit.
It's a complicated exploit. There's two pieces to it. The driver does not handle if there's two sensors connected. Step 1, we remove the type cover. And step 2, we connect the hard part is finding that, stick it in. So, if you lost your finger, we can borrow the stick for you.
On sale.
So what did we learn?
We learned that the landscape's pretty diverse with fingerprint auth, right? We ended up with full authentication bypass on all 3 targets, which we'll take. Yeah.
Good. Yep.
There's definitely an inconsistency between vendors, right? That's there was a difference in code quality, and it seems like a misunderstanding of SDCP by developers. Lots of logical issues. Also, just that most of these sensors support other OSs, not just Windows. Again, SDCP is quite narrow in what it's trying to protect. So you've got all this other attack surface of commands or APIs that are also supported by the sensor that lead to potential issues.
Yep.
The also unauthenticated attack surface, not authenticated by SDCP.
Yeah. So basically, you really need to know that SDCP is enabled. It's always not obvious, but there's instructions. And I think in the newer versions of Windows, like 11, it's better. This was on Windows 10 what we did.
Right. And so, yeah, as far as from a future work perspective, from the hardware and firmware research perspective, we also noticed a number of things that we didn't really get to dig into a lot in this work. So the firmware seems pretty brittle in general. Mm-hmm. Lots of potential for memory corruption at the sensor side itself. You look at it funny and it crashes.
We made the sensors boot many times during the research.
Also, the potential for hardware vulnerabilities put the secrets at risk. So while SDCP prescribes certain specific things, there's always a potential where you could debug with JTAG or decap the chips in order to extract or insert secrets, directly access storage, things like that. Also, there's not anything prescribed to have security between the actual sensor itself and the onboard SOC, right? So there's the potential there for a MitM. Also, other targets, Linux kind of supports fingerprint stuff too.
That's story different.
And Android and Apple, that kind of thing. So I want to thank everybody, the MORSE team for sponsoring this work and also letting us talk. A lot of times we don't usually get the opportunity to talk about some of the stuff that we do, and so it was great to get the green light for that. The Windows Hello team too were great throughout this process, and then our team as well. Some others like Chris Williams, Ricardo. So yeah, thanks to everybody involved, and
that's what we had today.
I think that's it.
Yeah. Thank you.